Initially, there was an infinitely dense mass of matter. This mass underwent an explosion that gave rise to the formation of atoms, molecules, stars, and galaxies that we can observe today. For decades, this has been the explanation offered by physicists. However, recent research has introduced a new perspective that suggests that the universe does not have as early an origin as initially believed. Instead, it may be part of a cyclical process in which the universe goes through a series of cycles of expansion and contraction, possibly in an infinite loop. Brian Cox, a renowned physicist, has also raised doubts about the Big Bang theory, arguing that something cannot arise out of nothing. This questioning adds an intriguing element to the discussion. In addition, research from the James Webb Telescope has revealed information that contradicts the idea that the Big Bang marked the absolute beginning of the universe. This leads to the fundamental question: if the Big Bang was not the beginning of the cosmos, then what was? Join us on this journey to the beginnings of the cosmos, where we will explore the frontiers of the Big Bang and answer this question and many more. If you are interested in keeping up to date with news about the universe and its surroundings, subscribe to our channel, hit the like button, share this video to reach more people, and turn on the notification bell. Scientists have developed a detailed understanding of the universe in its earliest stages, known as the Big Bang theory. According to this model, the universe was much smaller, hotter, and denser than it was in the past, approximately 13.8 billion years ago. During that period, all the elements that make up our world were formed in a matter of minutes. In this theory, our universe, including stars and galaxies, was once as tiny as a peach and had an extremely high temperature of over a quadrillion degrees. Interestingly, this astonishing narrative aligns consistently with all current observations. Astronomers have investigated everything from the remnant electromagnetic radiation of the early universe to the abundance of the lightest elements, and have found that everything agrees with the predictions of the Big Bang. To the best of our knowledge, this description fits the reality of our universe perfectly. However, despite its apparent robustness, we know that the Big Bang theory is not the complete picture. There's a missing piece to this puzzle, and that piece is an understanding of the first moments of the universe. This challenge is due, in large part, to the limitations of the physical theories we currently employ. The combination of general relativity and high-energy particle physics provides us with a valuable conceptual framework. However, as we delve deeper into the initial moments of the cosmos, the mathematical complexity increases significantly, reaching a point at which our current methods cannot provide meaningful solutions. One of the indications of this difficulty is the existence of a singularity, a point of infinite density at the beginning of the Big Bang. This notion suggests, literally, that the universe was once compressed into an infinitely small and dense state, which seems to be absurd. To address this challenge, we need to explore new frontiers in physics, develop an approach that overcomes these limitations, and provide a more complete understanding of the first instance of the universe. Our current instruments and theoretical frameworks are not robust enough to address this challenge, so we need to develop new physics that can encompass and explain gravity and the other fundamental forces at extremely high energies. This is precisely where string theory comes into the picture. This theory aspires to be a physical model capable of unifying gravity with the other fundamental forces, especially at ultra-high energies. In essence, string theory posits that it can provide an explanation for the first moments of the universe. Within string theory arises the concept of an ekpyrotic universe, which takes its name from the Greek word meaning conflagration or fire. This idea suggests that the Big Bang, as we know it, was the result of an earlier event, implying that it was not the absolute beginning, but rather a part of an ongoing process. Extending the notion of an ekpyrotic universe has led to the development of a related theory called cyclic cosmology. Although the idea of a cyclic universe has been considered for millennia, string theory provides a solid mathematical basis for this conception. In the framework of cyclic cosmology, the universe functions as if it perpetually oscillates between large explosions and collapses in an endless cycle that extends infinitely into the past and future. This theory of cyclic cosmology was proposed by the eminent physicist Roger Penrose, who was awarded the Nobel Prize. Penrose was intrigued by a remarkable mathematical relationship between the early universe, characterized by extreme density, heat, and smallness during the Big Bang, and the future state of the universe, which is characterized as extremely cold, expanded, and devoid of matter. The theory suggests that these two states become mathematically identical when pushed to extreme limits. Although it may seem paradoxical, the total absence of matter could be the driving force behind the creation of all the matter we observe in the universe. From this perspective, the Big Bang originates from what remains, almost imperceptibly, after all the matter in the universe has been consumed by black holes that eventually evaporate into scattered photographs in a vast void. The universe emerges from what, from another point of view, essentially approaches nothingness, although this nothingness is still a form of something that constitutes a physical universe, albeit an empty one. The mystery lies in how this same state can be interpreted as both a cold, empty universe and a dense universe, depending on the point of view. The key to this understanding lies in a complex mathematical technique called the conformal transformation, which is a geometric transformation that changes the size of an object while retaining its shape. Roger Penrose showed that the cold, empty state and the hot, dense state can be connected through this scale transformation, aligning their spatio-temporal structures. Despite their differences in size, they can be identical in essence, despite having different sizes. However, Penrose argues that the concept of size loses its relevance under these extreme physical conditions. In cyclic cosmology, the sequence of events unfolds from an old, cold state to a young, hot state. The presence of the hot and dense state is the result of the previous cold and empty state. However, this casual relationship does not follow the usual pattern in terms of time, since in these extreme states, both size and time lose their conventional meanings. The cold empty state and the hot dense state exist on separate timelines, which means that, from the perspective of an observer within his own time frame, the cold empty state would continue indefinitely. Physics and philosophy are intertwined in this realm of cyclic concepts. Cosmology provides speculative and detailed explanations for the origin of these cycles. However, even if Penrose's ideas gained support in cosmological advances, a deeper philosophical question still lingers about the origin of physical reality itself. How did these cycles come into existence? This leads us to ponder the reason for the existence of something rather than nothing, which is one of the fundamental metaphysical questions. For our purposes of discussion, we will focus on explanations within the realm of physics, and there are three possibilities to consider in exploring the origins of these cycles. First, there may be no physical explanation at all. Second, there could be an infinite series of cycles, where each cycle represents a different universe, and the initial quantum state of each universe is somehow determined by some aspect of the universe that preceded it. Finally, there is the option of a single cycle and a repeating universe, where the beginning of the cycle is explained by some feature of its own end. These possibilities are attractive because they avoid the need for uncaused events and provide a more complex explanation within the physical framework. In the realm of physics, Penrose proposes the idea of an endless sequence of cycles influenced by his interpretation of quantum mechanics. In quantum mechanics, a physical system exists in multiple states simultaneously until it is observed, at which point it randomly collapses into a single state. Penrose suggests that each cycle is influenced by random quantum events that give rise to variations between cycles. This concept opens up promising possibilities for experimental physicists, as it suggests the possibility of detecting subtle traces or anomalies in the remnant radiation of the Big Bang.
A serious nag has arisen in the field of astronomy due to the latest findings of the James Webb Telescope, which have illuminated previously unknown aspects of our universe. The continued discoveries of this telescope are having a profound impact on our understanding of the universe. The telescope, by casting its gaze into the remote past, revealed secrets that were previously beyond our perspective ability. A recent surprising discovery has challenged our fundamental understanding of the universe, indicating that we may be completely wrong about its size. In a recent paper, scientists have exposed that new images captured by the Webb Telescope have identified objects that existed only 120 million years after the Big Bang. This not only challenges what was previously believed, but also calls into question the foundations of the standard cosmological model. Astronomers admit they did not anticipate discovering something of this nature in the images captured by the Webb Telescope. It appears that the universe is indeed old, but not infinitely old, a revelation that has surprised many, refuting the idea that the universe must have an infinite age without a starting point. This discovery has shown that our intuition has been wrong most of the time. We face the uncertainty of not knowing what else the universe has in store for us. Even when the Webb Telescope looks as far out into space as possible, it only manages to observe a distance of about 46.5 billion years. The radius of the universe we can observe, known as the Hubble radius or Hubble sphere, defines the limit of what we are able to see from Earth. The most remote galaxy discovered so far, the IES galaxy identified by the Webb Telescope, lies within this region. The Massey galaxy, the most distant galaxy found so far, existed approximately 450 million years after the Big Bang and also lies within this Hubble sphere. While we know that our universe is expanding, what is even more intriguing is that this expansion is accelerating. As the universe expands, the Hubble sphere grows, allowing the visibility of objects beyond its boundaries. However, at the edges of the sphere, the expansion is happening faster than the speed of light. This means that although the Hubble region does not expand, when we observe extremely distant objects, the speed of expansion of the space between us and those objects exceeds the speed at which the light emitted by them can reach us. Therefore, light from very distant stars and galaxies is moving away from us at a faster rate than it can reach, due to the stretching of space between us and those distant objects caused by cosmic expansion. The Hubble sphere will stop growing once it reaches the limit of the cosmic horizon, thus defining what is known as the observable universe, a region that shows us the maximum extent of our vision within the universe. The observable universe is like an imaginary sphere that surrounds us and has a diameter of approximately 93 billion light years. This measurement represents the maximum distance to which we can see galaxies and stars. Light coming from within the sphere has had to travel for a considerable time to reach us. However, anything beyond the sphere will not be visible to us, even if we were to use the most powerful telescope imaginable. The reason is that the light emitted by these objects has not yet reached us. This situation raises an interesting question about the total size of the universe outside the limits of our observable sphere, and in reality, we do not have a precise answer to this question. Although our current cosmological theories have provided mathematical estimates, we still lack sufficient information to be certain. We may never be certain. It has been estimated that the entire universe is at least 250 times larger than what we can observe. Some research has suggested that the total size of the universe could be astronomically enormous, with estimates that it could be on the order of 10 to the power 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 of 10 to the 122 times larger than our observable universe. This number is incredibly large, with an enormous number of digits. Despite these estimates, the uniform distribution of matter in the universe and the uniformity in the temperature of the cosmic microwave background suggest that our universe could be infinite in size, although this conclusion remains a theoretical possibility rather than an absolute certainty. When we look out into the extremely far distances in space, we are actually observing events that occurred a very long time ago. The galaxies we see near the Hubble sphere are not galaxies that exist in the present, but are galaxies that existed billions of years ago, according to our standard cosmological model. According to this model, approximately 14 billion years ago, the observable universe and everything beyond it would have been concentrated into an extremely small point, which we called a singularity. However, this notion of a singularity compressed into an infinitesimal point would be true if the universe were infinite. However, the evidence points to the universe being infinite, suggesting that it was always so, without a singular beginning. This would imply that the Big Bang occurred everywhere, meaning that the first galaxies did not form in a particular place in space, but formed everywhere in the universe, even beyond what we can observe. This idea raises the question of the starting point of the event that started it all. This question transcends science and enters the realm of philosophy. It is similar to the old steady-state model that held the idea that the universe has always existed without a beginning. This perspective was appreciated by figures such as Newton and Einstein, who believed in a universe that had always been there, without a beginning. Einstein initially rejected the idea of the Big Bang, but mathematical evidence led him to consider the possibility of a finite origin. Observation of cosmic microwaves throughout the universe suggests that the singularity is not the starting point from which everything emerged, but rather an infinite place where all matter, everywhere in the universe, came into existence approximately 13.8 billion years ago. So far, what I've mentioned explains the enigmatic nature of our universe. However, new discoveries from the Webb Telescope are challenging the estimated age of the universe. Each deep image captured by the Webb Telescope reveals unexpected surprises that force us to reconsider the conventional Big Bang model, which stipulates that our universe is approximately 13.8 billion years old. Until 2022, the most distant galaxy known was believed to be Sirius 93 316, but later studies revealed that it was that nearby galaxy that appeared more distant due to dust clouds. Recently, the James Webb Telescope has discovered the galaxy F200DV045, a high redshift galaxy candidate with an approximate value of Z20.4, which corresponds to about 168 million years after the Big Bang. If confirmed, this would be one of the oldest and most distant galaxies observed. This discovery, although it still needs to be confirmed with further tests, may require a revision of the standard model to obtain a better estimate of the age of the universe. In addition, massive galaxies have been discovered that apparently formed a few million years after the Big Bang, challenging our current understanding of how quickly galaxies formed in the early universe. Another significant finding was made with the help of the James Webb Telescope, revealing the presence of two black holes 700 million years after the Big Bang. This discovery suggests that the universe may be much older than previously thought, or possibly had no absolute beginning and has always existed. These revelations open up the possibility that the universe, seemingly infinite in size, may also have an infinite age. The Big Bang could have been just a moment in the evolution of this universe without a true beginning. However, more research will be needed to determine whether this idea of an external universe without a beginning aligns with our current scientific theories to effectively explain the unfolding of events during the Big Bang. Modern science explains the origins of the universe within the Big Bang theory. According to this theory, the universe arose from the explosion of the singularity. The singularity is a point in the fabric of space and time where the concentration of energy and matter becomes extraordinarily high, reaching almost an infinite level, while the spatial and temporal dimensions are reduced to near-zero values. However, recently the James Webb Telescope has made a bold announcement that the universe has existed uninterruptedly and that the Big Bang theory is wrong in its approach. If you're interested in keeping up to date with news from the universe and its surroundings, subscribe to our channel, hit the like button, and turn on the notification bell. The concept of singularity describes a state where neither time, space, nor matter existed. The question that arises is where this singularity came from, what preceded it, and what even triggered the event that culminated into the Big Bang. It is debated whether the universe has existed eternally or whether it had a definite starting point. The singularity that preceded the Big Bang event contained the entire mass present in the universe, and this resulted in the complete suspension of the flow of time. This aligns with the perspective proposed by Albert Einstein, which suggests that debating what happened before the Big Bang is meaningless, since the notion of a before had no place. The idea that the universe is not expanding in empty space may be difficult to conceive. This conception is based on a theory known as the Einstein theory of general relativity, which he developed in 1915, and which remains to this date our best description of space and time. This theory is the foundation for many of these interesting and peculiar ideas. The theory of general relativity is supported by evidence such as the expansion of the universe, which was discovered by American astronomers Hubble in 1929. In addition, there is the cosmic microwave background radiation, which is uniformly distributed throughout the universe and was discovered by the American scientist Spenzias in Wilson 1965. The discoveries support the basis of our current understanding of the evolution and the nature of the cosmos. This radiation emerged approximately 379,000 years after the Big Bang, in a period known as the hydrogen recombination era. According to the Big Bang theory, in its earliest moments, our universe was tiny, no bigger than an atom. In times past, the notion of nothingness was a sustainable state. Asking how long it lasted is irrelevant, since during this period, the concept of time simply had no existence. In this era, our world emerged from a random quantum fluctuation that emerged from the void, which represents a significant level of depth. Perhaps a question of greater relevance might be whether this quantum fluctuation was truly random, as Einstein famously put it in his famous phrase, "God does not play dice." With this notion in mind, it is interesting to reflect on the implications of this. What prevents another small fragment of energy-filled void from appearing again, leading to a new Big Bang? There is a possibility of this occurring with a 100% probability, which could annul the existence of mankind. In the multiverse theory, the emergence of life occurs through a natural phenomenon in which universes with parameters conducive to more black holes will have a greater chance of generating offspring, thus increasing the probability of life being present in those universes. Recently, renowned physicist Brian Cox explored the fundamental question of how the universe began. Cox presented the Big Bang theory, but in return, challenged the conventional perspective by introducing a fascinating approach, the idea of the existence of a time before the Big Bang. This intriguing notion expands our understanding of the origins of the universe. The notion of a pre-Big Bang universe connects to the theory of cosmic inflation. According to this theory, the universe underwent an exponential expansion in an extremely short period after the Big Bang. This significant growth allowed the universe to become uniform indeed, explaining its observed homogeneity on a large scale. Although inflation remains a fundamental part of the prevailing cosmological model, Koch's idea of a pre-Big Bang state adds a layer of complexity to the chronology of the evolution of the universe. One question that arises is what could have caused this primordial energy to trigger such a sequence of events? Could it be the result of interactions between forces that we do not yet fully understand? Koch's ideas about the time before the Big Bang are supported in the work of Roger Penrose, an outstanding mathematician and physicist who was awarded the Nobel Prize in Physics for his contributions to the understanding of black holes. Although his focus is on black holes, Penrose also introduces the concept of eons, which occurs in a cyclic framework. Each eon begins with a Big Bang, followed by a period of expansion, contraction, and finally a big crunch, in which the universe returns to its original state. This cyclic cycle sets the basis for a new eon, perpetuating itself indefinitely. Penrose's eon theory revolves around black holes, celestial objects of enormous gravitational force that emerge from the collapse of massive stars. Over time, these black holes evaporate through Hawking radiation, releasing energy. Penrose speculated that dead black holes from earlier eons may still exist today, leaving possible imprints in our observed universe. These remnants Penrose called Hawking points, in honor of Stephen Hawking and his contribution to the understanding of Hawking radiation. The late physicist Stephen Hawking's proposal could offer clues supporting the existence of states prior to the Big Bang. Roger Penrose's idea of Hawking points could represent a potential clue to the existence of a pre-Big Bang universe. These enigmatic points, which are about 8 times to the size of the Moon, refer to slightly warmer areas in the sky that can be detected by advanced observational techniques. While Hawking's concept of the dots stands out in the scientific conversation and highlights the fluidity of our understanding of the beginnings of the universe, the discussion also highlights the importance of scientific exploration and the potential for paradigm-shifting discoveries in the future, as with any revolutionary scientific proposal. Brian Cox and Roger Penrose's exploration of a time before the Big Bang faces challenges and controversy. Critics argue that the concept of a pre-Big Bang universe remains speculative, as it lacks direct observational evidence. In addition, the cyclic nature of Penrose's eon theory raises questions about the conservation of energy and the ultimate fate of the universe. Some skeptics question the feasibility of an infinite cycle of eons, as this could conflict with the laws of thermodynamics and other fundamental principles of physics. Now let's delve into another related theory, the multiverse hypothesis in cosmology. This notion suggests the existence of multiple universes, each with its own physical laws, constants, and properties. Well, the basis of this idea lies in the belief that our universe could be one among many in a vast and diverse multiverse. The concept of the multiverse has gained momentum as a way to explain certain aspects of our universe that seem to be finely tuned for the existence of life. Scientists have observed that the fundamental constants and physical laws governing our universe appear to be carefully balanced to allow the emergence of life as we know it. From this observation, some have proposed the anthropic principle, which holds that our universe has the characteristics it does because it must be capable of hosting intelligent observers like us. And well, let us know your opinion in the comments box. If you liked the video, remember to like and subscribe, and I'll see you in the next one. Thank you so much for watching.